Hello, I'm Philip Schepper, and I'm going to talk about the paper Fine-Grained Complexity of Regular Expression Pattern Matching and Membership. So I guess everyone should know about regular expressions. So what are they used for, or why are they so important concept for computer science? First, they are mainly used for text analysis or text manipulation, meaning we search for some specific pattern in a text, and we want to replace this by some other text, as for example the Unix tools grep and z do. But they are also used for network analysis, and not only in computer science but also in biology, for example to search for proteins and DNA sequences, which can also be seen as text strings, and very surprisingly they can also be used for human-computer interaction. So what are the problems I want to consider? First, we have the classical problem, the so-called membership problem, where we are given a text T and a pattern P, and we just want to check whether this text is generated by our pattern P, so is the text in the language of the pattern. Then we also have a quite similar problem, the so-called pattern matching problem, there we are also given a text T and a pattern P, and we want to check whether there's some substring of our text that is generated by the pattern. So we don't want to check whether the whole text is generated by the pattern, but just the substring. So to simplify notation, we define the matching language, which consists of all words where some part of the words are matched by the pattern P. So now the natural question is, how fast can these problems be solved? And I guess everyone should know that the answer to this problem is O of n times m, where n is the text length and m is the pattern size. But of course, we can also ask for more. So is it possible to improve this algorithm, or is it maybe the best? So can we get a little O of n times m algorithm, or is actually omega n times n the running time we can achieve? So today I'm going to give a short introduction and show the results of the paper, then give an example for an upper bound and an example for the lower bound. So to get everyone to the same base, if I talk about regular expressions and symbols, what do I mean? First, of course, we have the easiest regular expression, which is just consisting of a symbol sigma, and it represents exactly this language. Then we have the alternative denoted by this bar here, and it's just a union of the two languages of the two patterns. Then we have the concatenation denoted by the circle. We have the Kleene plus and the Kleene star, naturally denoted by the plus and the star. And if not stated otherwise, we assume that n is the text length and m is the pattern size. And we define the pattern size as the number of operators and symbols in the pattern. And in the following, we also extend the definition of the alternative and the concatenation to more than two subpatterns. So what are the current results? There's the classical O of n times m algorithm by Thomson from 1968. And it took several decades to get an improvement for this algorithm. And the first improvement was by Myers using the so-called 4 Russians technique. And he was able to shave one log factor from the quadratic running time. Then Bille and Turrup gave another improvement, and they were able to shave 1.5 log factors. So now the currently best algorithm has running time O bar of n times m divided by log to the 1.5n, where this O bar hides polylog log n factors. But there are also results from the lower bounds, and the first lower bound was by Bacchus and Indig, and he showed that there are no polynomial improvements over this quadratic running time unless the strong exponential time hypothesis is false. Then by Abbott and Brinkman, there was another lower bound shown, ruling out log factor improvements, so one cannot shave more than 7 log factors from this quadratic running time using the so-called formula SAT hypothesis. And the consequence of this I'm going to explain later. So what you can see, if we take a look at these running times and this lower bound here, these bounds match up to a constant number of log factors. So sounds pretty good, but actually the problem is these bounds are for the general case. And maybe it can happen that we have somewhat easier patterns and we want to check how fast the algorithms for these patterns work. But of course, if we talk about easier patterns, we have to define some notion of easy. So this directly leads us to the definition of homogeneous patterns. And if we talk about a pattern, we can see it as a tree, or especially as a labeled tree. And we have the leaves of this tree are labeled with our symbols from the alphabet sigma, and all inner nodes are labeled with the operations or concatenation cleanly plus and cleanly star. And then we can define what a homogeneous pattern is. And we say a pattern is homogeneous if for every level of the corresponding tree, all inner nodes are labeled with the same operation. And then the type is just a sequence of these operations from the root to the deepest leaf. So now we look at an example. So if we consider this pattern here, we see that the plus is the outermost operation, and we make the plus or a node labeled plus as the root of the tree, and then we continue going down and decomposing the pattern and building the tree recursively. So as the next operation, we have a concatenation here, and then we continue until we get this tree. So as we can see, if we now check for every level, the first level has just one inner node, it's a plus. The second level has just a concatenation. If we go to the next level, we see, okay, here's not an OR, but this is a leaf, so it's not affected by our definition. And all the other nodes are labeled with an OR. If we go one level down further, we can see that all inner nodes are labeled with a concatenation. And on the last level, we have just symbols, so we don't have to consider this level. And then we see this pattern is actually a homogeneous pattern, and further its type is plus concatenation or concatenation, and the depth is 4. So this is an example for a homogeneous pattern. So what are not homogeneous, or patterns that are not homogeneous? For example, this pattern here, we have a concatenation as outer operation, and then we have on the next level a star, an alternative, and a clean plus. So this pattern is not homogeneous, and so it does not allow to define a type. So now as we have the homogeneous patterns, there are more results. So we have the general bounds shaping 1.5 log factors, and the lower bound by Abbott and Brinkman that we cannot shave more than 7 log factors. So now if we take a look at this homogeneous pattern, one can figure out that several common problems do only require homogeneous patterns. So they don't require very general ones, but pretty simple structured patterns, for example, for the dictionary, superset, and string matching. And most surprisingly, these problems can be solved in near linear time. So it seems like our definition of homogeneous patterns was too strong. So one could assume that all homogeneous patterns can be solved fast, but actually this isn't the case. There's a dichotomy result for homogeneous pattern types and classifies the pattern types into easy and hard. And for the easy ones, we have actually strong subquadratic time algorithms. And for the hard pattern types, we have a lower bound based on SETH that we cannot shave more than, or that we cannot shave a polynomial factor. And most surprisingly, it suffices to analyze a few number of pattern types that also have a constant depth. So normally we would have to consider all homogeneous pattern types, as there can be infinitely many combinations of the patterns. We would have to classify infinitely many types, but actually there are reductions between the types. So it suffices very, very little number of homogeneous patterns. So now the natural question is, what about these homogeneous types and the lower bounds for the general patterns? So can we transfer this lower bound we have seen here to these homogeneous patterns, or are there maybe algorithm improvements for the algorithms for the other pattern types? So is there, for example, a pattern type for which this algorithm is not optimal? And this is exactly the question I addressed in this paper, and the result can be seen here. So there's a classification of the different pattern types one has to consider. So the classification of these hard pattern types here, not allowing polynomial time improvement. And they can be classified into these four categories. And for considering pattern matching and the membership problem. And the first result is an improved upper bound for these two types here for the pattern matching, and for these two corresponding types for the membership problem. And this algorithm has a super polylogarithmic improvement. So it's actually the currently fastest algorithm for pattern matching for these types, and also the best we can hope for under SETH, as we have here a lower bound ruling out polynomial time improvements. So for the remaining two cases, for these two here, we show tight lower bounds, meaning that it's not possible to shave more than a constant number of log factors. And for these two types, general algorithm is optimal. And also one could say that a classical algorithm by Thompson is still optimal up to a constant number of log factors. So overall, just to summarize this gives us a tight dichotomy for these homogeneous pattern types where we are ignoring log factors. So now let us take a look at an example for the upper bounds. And for this, we just take a short look at a very general concept of the polynomial method. And it was originally used by Rasperev and Smolensky to show circuit lower bounds. And it's a technique to transform Boolean circuits into polynomials. Williams used this method to improve the algorithm for APSP, the all paths shortest path problem, and it yields a super polylogarithmic runtime improvement. And the main idea of this problem is to solve the task on many subproblems in parallel by using fast matrix multiplication and this polynomial method. So this polynomial method can not only be applied to APSP, but also to other problems. And here we focus, or we use the so-called orthogonal vectors problem. And for this, we are given two sets U and V of binary vectors in d dimensions. And the question is to ask whether there's a vector from each set such that both vectors are orthogonal. So for each dimension, there's one vector where the entry is 0 in this dimension. And using this polynomial method, Chan and Williams were able to show that for small dimensions, so roughly of the order 2 to the square root log n, orthogonal vectors can be solved in time n squared divided by 2 to the square root log n. So how do we use this for our algorithm, for the fast pattern matching algorithm? So for example, we focus here just on this pattern or concatenation or, and here you can see an example of this. And now the main observation is that we can split this pattern into independent subpatterns. So for example, this pattern BD completely behaves completely independent from the pattern here. And by this, we are able to classify these subpatterns. And for this, we define some threshold f, which is roughly of the order 2 to the square root log n. And according to this, we split the subpatterns into two groups, namely the large ones, where we match more than f symbols, and the small ones, where we match at most f symbols. And then for each of the large patterns, there are at most m divided by f many. We first observe that they are all of type concatenation OR. And for this pattern type, there is a near linear time algorithm. And we run this algorithm simply on all large patterns. And by this, we already get a running time with a super polylogarithmic improvement. But of course, we also have to consider the small pattern types. And for them, we give a reduction from pattern matching to OV. And we keep the dimension small. And by this, we directly get an improved algorithm by the lemma we have seen on the slide before. So how does this reduction work? So for simplicity, we assume that all subpatterns have the same length or match exactly f symbols. And then if you take a look, what actually is a match? It's just checking whether there's some subpattern Q and an offset I, such that we can align this pattern to the text starting at some position I and the following F symbols are matched to the pattern. So by this it should be fairly easy to see that we use all strings or substrings of our input text t with length f as one set of the vectors, and we want to use the patterns as the other set of vectors, or the subpatterns as the other set of vectors. But of course, this does not directly work because we have to encode these vectors in binary. And for this, we use the following approach. We use the characteristic vector of our set of our alphabet sigma. And for example, consider that sigma is ABC and our text ti at some position ti here is A and the pattern is A or B. Then using the characteristic vector of our alphabet, we have a 1 here, and the text has no B, it's not a B and not a C, we put zeros here, and the pattern can match an A and a B, so we put 1s here and a 0 at position Z. And now as a final step, we simply flip the pattern vector, so it becomes 0, 0, 1, and now we can see this text, or this vector here is orthogonal to this vector here, and this implies that our text can be matched by the pattern. So what do we have? We have finally, as a result, we have n text vectors and we have at most pattern vectors because they're at most f patterns, at most m patterns. As we know, each pattern matches at most f symbols and our texts are of length f. We have a dimension of f times the size of sigma. And if we assume that sigma is small, so 2 to the O of square root log n, we know that we have this dimension constraint fulfilled, and we can use the fast algorithm for V to solve this problem. If the size of the alphabet is larger, we use Bloom filters to reduce the dimension to still be able to apply the fast algorithm for V. Okay, that's it for the upper bounds part. Now we come to the lower bounds, and for this we first have to start with the satisfiability problem. And as we have seen in the introduction, there's a lower bound based on STH, ruling out polynomial improvements. But we want to rule out log factor improvements, so we need some strong assumption, and this directly leads us to the definition of a monotone De Morgan formula, and this is just a node labeled 3, and each inner node is labeled with an AND or an OR, so these are the gates, and each leaf is labeled with a variable, the so-called input gates, and we say that the size of this formula is the number of leaves. Then we also get the definition of the formula pair problem, and there we are given some monotone De Morgan formula, and we further assume that the inputs are used exactly once. And we also have two sets of half assignments, and both have size n and m. And the task is simply to check whether there are two half assignments, one from each set, such that the formula is satisfied on these two half assignments. So is f of a comma b true? So and there's the formula pair hypothesis, which is based on the earlier mentioned formula set hypothesis. And it essentially says that we cannot solve formula pair in this running time for any k, where s is the size of the formula and n is the number of half assignments in both subsets. So and we use this to show our lower bound for the pattern matching problem, and we reduce formula pair to pattern matching. And by this we want to code this formula here, or want to model this formula here by a text t and a pattern p. And for this we first focus on the last part here, so that we fix the half assignments a and b, and we want to design a text t and a pattern p such that the text is matched by the pattern if and only if the formula is satisfied on these two half assignments a and b. And for this we encode the formula inductively. And again, we just focus on one pattern type. Here we have the concatenation plus concatenation, so we can have the cleanie plus on a whole text. So for encoding the input gate, we observe if we read a variable from the half assignment A, we write down the text T and the pattern P like this. And then we can see the text is matched by the pattern if and only if AI is set to 1. we can define the text and the pattern in an analogous way if the assignment from the second half assignment is read. So for the AND gates, we recall that we have to satisfy both subformulas, and for this we write down the text as T1, T2, and the pattern as P1, P2. Then we can ensure that P1 has to match T1 and P2 has to match T2. And just to avoid problems, we add some separator gadget in between that allows or forces us to match these two G's to each other. So P1 cannot match some part of T2 or P2 some part of T1. So by this we get that there's a match if and only if both subformulas match the text. So unfortunately, this is not sufficient for the OR gate, because there we also need some universal text U and a universal pattern Q. They are defined in such a way that our pattern P can match the universal text U always, and our universal pattern Q can match the universal text and the normal text independently from our half assignments. Now we can move on to the OR gate, and for this we start in a similar fashion as for the AND gate. So T1 has to match by P1, T2 has to match by T2, but actually as we have an OR gate, it can happen that one subformula is not satisfied. So we have to modify our pattern such that we can choose between two alignments. So for example, if we choose this alignment here, we match P1 to T1, and then we use this universal pattern Q2 to match the text T2. But then we can also see that this part here does not match part of the text. So we have to pad our text. And for this, we use the universal text, as we also can have to make sure that it works for the other alignment. We have to append this text to the other side. And now we have the same problem. There's some part of the text that is not matched. So we have to pad our pattern, and we do this in the same way. And we add the same text, we pad it to the text, to the pattern on both sides. Now one can say, oh, this will continue forever, because if we add something to the text, the pattern will be too short, and if we pad our pattern, the text will be too short. But actually, if we add one more round for the text, we can see that we have the same groups here. So this group is the same group as here, and for the pattern, we have to on the other side of the text, we have the same situation, and then just suffices to add a linear plus to these groups of the pattern. And by this, we don't have to add more parts to the text. And we can simply stop and conclude the definition of the text and the pattern for the OR gate. Of course, we also need the universal text and universal pattern, but they are actually the same as the normal text, but we replace the role of T by the role of U and Q. So what about the size bound? We can directly see that the size of our universal text, the normal text, and universal pattern is always the same, because they only differ at these positions here. And we can see that the pattern is always shorter than the universal text. And this directly leads us to the conclusion that we have this size bound here, 5 to the depth of the formula times s log s. And this 5 to the depth comes from the fact that we have 5 times subformulas here written down, and we have to go the depth of fg many levels down, and so this factor of 5 propagates in front, and we have this factor of s log s here because each level can introduce, or each formula introduces s log s many new symbols because of these separators here. Recall we want to encode this formula here. We want to check whether there's an A and a B satisfying the formula. And what we have seen already is how we do the check for two given half assignments. So it remains to choose this A and a B. And this is what we do in the following. So for this, we define the text as this and the pattern like this. So we have here some parts for the alignment in the beginning and the end. And in this pattern group, we can choose here whether we match the universal pattern to the text or whether we actually perform a evaluation of this formula f here. And by this, we actually get that this correct construction is correct. So the text is in the matching language of the pattern if and only if this formula can be satisfied. So What about the lower bound? No, we get a text length of the pattern size is n times 5 to the d s log s. And we see we have an exponential dependence on the depth here, but we can get rid of this by using some depth reduction technique by Bonnet and Bass, for example. So our depth becomes logarithmic in the size, and the size blows up by a quadratic factor, but this does not matter too much because we have here only a polynomial dependence on the size. So our final text and the final pattern are of size s times s to the 15. And now we can assume that we have such an algorithm for concatenation plus concatenation pattern matching, and now we simply plug in the values and get such a running time. But if we take a look again at the formula pair hypothesis, it says that we don't have an algorithm that for all k we don't have such running time. And actually, if we choose k equals 30, we see that this algorithm is not possible. So we get a conditional lower bound of that we cannot shave more than 92 log factors, assuming the formula pair hypothesis. So let's conclude. And we classified in the paper the remaining hard pattern types into 4 categories. It was known before that we have a lower bound based on STH that roots out polynomial improvements. And now we actually have shown for 2 groups of patterns that there are super polylogarithmic improvements. And for the other 2 pattern groups, we have shown a conditional lower bound based on the formula pair hypothesis that we cannot shave more than a constant number of log factors. So the algorithm that was best before is still optimal up to constant number of log factors, and we get a tight dichotomy for the hard pattern types.